What's not success? Any other number. So the probability of success here is 1 in 6. A random card from a deck of cards with success defined as an ace. So the probability of an ace is 4 out of 52, which is 1 out of 13. So failure is 12 out of 13. The outcome from a door-to-door sales approach. So maybe you go to 100 doors. Now 1 in 15, you must be selling something easy to sell. So you've got a finite number of, well, no, forget about the finite number of doors. We're just looking at a single trial, going to a door, success is making a sale, probability of success 1 in 15. Another one, a single trial is, you look at a random shopper in a shopping queue, if they get served in less than 2 minutes, that's a success. And then just to show that success doesn't have to be good, take a person and have success defined as having killed someone. So success doesn't have to be good. Did you kill someone?
Huh?
Did you ever kill someone?
We could hit them.
So, failure, you know? And if he said he did kill someone, that'd be a success. Okay?
There's tons of people like you're affected by anything in this class.
Okay. Now, so here, the way this is done is, so if you, X is the number of successes in a number of independent, you're assuming independent, identically distributed, just means that the probability of success doesn't change. Then if X is, we've changed this to the number of successes. Then you have a probability distribution, or basically a formula for the probability that the number of successes is equal to a number here, K. So what you have is, say, K successes. So you're going to have success and success and success P times, K times. So you're going to have P by P by P by P by P, K times. And then if there's K successes out of N, the rest of them, we'll just put some nice numbers under here, okay? So say, for example, you have N equal to, we'll go with the door-to-door sales in this story. So say N is equal to 100. So you go knocking on 100 doors, and you're interested in the probability of, say, 2 successes. And we'll say the probability of success here, we'll run with 0.07, say. So you've got 100 doors you're knocking on. What's the probability that you make 2 sales? Now, probability of success on the door is 7%, so you actually expect to make 7 sales, so this number would be quite small. So if you want, so here say X is the number of successes, number of sales, and you're interested in what is the probability that the number of sales is 2. So if you're kind of doing it like we did with the plants, in a second we're just going to use the formula, but if you're doing, say, the plants, the way we set it up was, okay, imagine you make sales on the first 2 doors. What's the probability of a sale on the first door? And the second door? 0.07. It's the same. And what's the probability that you fail on the third door?
0.03.
93, yeah. And then fail, and fail, and fail, fail 98 times. So you're going to have 2 successes and 98 failures. So success, and fail, and fail, and fail, and fail, and fail. And the and is going to mean multiply. So what you're going to have is you're going to have...
JP, what did you say, success in the second door?
It's the same. It's always going to be the same.
It's the same, you're knocking on 99 doors and the first door is gone.
Say that again?
You're knocking on 99 doors after the first door is gone.
Yeah, I'm not saying there's 7, I'm not saying that you definitely make 7 sales. I'm saying that you keep knocking on a door and independently you have a 7% chance each time. The most likely is 7, but it doesn't have to be 7. It's like flipping a coin. Flip a coin 10 times. The most likely is 5 heads, but it doesn't have to happen. You can have 3 heads and 7 tails.
You can't get Christmas on so.
Well,
Look.
so the or is always going to be plus here, and the and is going to be multiplied. It is, even though these questions are technically harder, there's less tricky bits in them. So if we had success and 98 failures, we should be multiplying probability of success by probability of success 0.07 by 0.07. So that would be 0.07 squared. And we would have fail and fail and fail and fail 98 times. So 0.93 multiplied together 98 times, which is 0.93 power of 98. Now that is only, now by the way, with these large numbers, no rounding. So if it was something like 1 out of 15, you have to use 1 out of 15, not point whatever. Because when you take some power of 98, rounding errors gets really, really bad. Now that's only success, and 98 failures. There's loads of other ways that you could have 2 successes. In fact, the number of ways is, from the 100 doors in front of you, how many ways can 2 of them be success? The answer is 100 C2. This is just another way of writing 100 choose 2. So I'm saying this is probability of success on the first 2 and 98 failures. But it's the same as if you have success, failure, then success, and then failures. It's just going to be, whatever way you do it, there's going to be 2 0.07s and 98.093s. However way the 2 sales are made. And then the question is, well, how many ways can you make 2 sales? Well, it is the number of ways that from 100 you can choose 2. And this is just exactly the same as this form up here. N equal to 100, K equal to 2, P 0.07 to the power of 2, 0.93 to the power of 98. And as I said, we're expecting 7 sales, so this probability should be pretty small. So I do 100, choose 2.
See, when you have in the brackets there, the 100 over the 2, that's 100 choose 2, is it?
Yes.
Yeah.
Yeah. So that means 100. It's not. It's not.
It's not 100 over 2, like that. Yeah.
This comes out, by the way, at about 2%. So there is a chance. That's probably pretty good. You're expecting 7 that you have in the dog day. 0.01978. Okay. So if we've got a binomial distribution, and the question will say binomial, it'll say assuming it shouldn't have to, but it will. If you want to find the probability that something is equal to something or something like that, you're going to use this formula. Okay, so we'll do a few examples. Now, the or stuff, the and stuff,